All right, let's dive into the world of composites. We're going to uncover how these materials are engineered for strength, lightness, and, all sorts of other cool properties.
Sounds good.
We've got a textbook chapter as our source material today, ready to unpack this whole fascinating field.
Perfect.
To kick things off, what exactly are composites? I feel like I've heard the term, but I couldn't really explain it to someone.
Well, you can think of composites kind of like a superhero team. Each material brings its own special ability to the table.
Oh, I like that.
Yeah, so they're formed by combining at least two different materials, a matrix and a dispersed phase. And this creates something even stronger than the individual components.
So it's not just mixing things randomly. There's an actual strategy involved.
Oh, absolutely. It's about harnessing what we call the principle of combined action. A classic example is pearlitic steel, where strong but brittle cementite layers are interspersed with these softer, more ductile ferrite layers. So the result is you get this balance of strength and ductility that neither material could achieve on its own.
I see. So it's like getting the best of both worlds. This principle seems pretty fundamental to, engineering new materials in general.
Yeah.
So how do we, categorize these composite powerhouses? What are the main types out there?
Well, your textbook outlines three main categories. You've got particle reinforced, fiber reinforced, and structural composites. Each category has, its own unique characteristics and applications.
Let's break them down one by one then.
Yeah.
So first up, particle reinforced composites. What's the deal with those?
Okay, so in particle reinforced composites, you essentially have particles that are roughly the same size in all dimensions, dispersed throughout a matrix.
Okay.
Think of it like adding sprinkles to a cake batter,
All right.
but obviously with a much more strategic purpose here.
Yeah, I was going to say.
It's all about those particles and how they interact with the matrix.
Right.
And there are two main subtypes. You've got large particle and dispersion strengthened composites. So in large particle composites like concrete, the particles are big enough to actually share the load with the matrix.
Oh, that's interesting.
It's like having a bunch of tiny weightlifters embedded in the material helping to bear the stress.
That makes a lot of sense. Concrete is everywhere, and I definitely wouldn't have thought of it as a composite before.
Yeah, it's a great example, right? Now, with dispersion-strengthened composites, things get a little bit more subtle. So the particles here are much smaller, almost at the nanoscale.
Wow.
And they work by hindering the movement of dislocations. These are like those tiny imperfections that can cause materials to deform under stress.
So it's like having these tiny invisible guards, protecting the material from weakening?
Exactly. And this mechanism is why materials like TD nickel, which is strengthened with tiny thoria particles, are so resistant to high temperatures. They can handle the heat because those dislocations are kept in check.
That's pretty amazing. Now, how do engineers predict the strength of these particle reinforced composites? I mean, do they just mix things up and see what happens?
Well, there's definitely a lot of science behind it. Equations like the rule of mixtures, which you'll find as equations 16.1 and 16.2 in your textbook, help predict the elastic modulus of a composite based on the properties of both the matrix and the particles.
So it's like a recipe, but with very precise measurements.
Absolutely. Getting the proportions right is key for achieving those desired properties.
Right. Speaking of recipes, let's go back to concrete for a second. Can you break down the ingredients and how they all work together to make this ubiquitous composite?
Sure. So think of concrete as a team effort between cement, sand, and gravel.
Wow.
The cement acts as the binder, holding everything together. The sand fills in the gaps between those larger gravel pieces, which ensures a nice, dense, and compact structure. And then the gravel provides the bulk of the strength, acting as the load-bearing pillars of the composite.
So it's not just chucking a bunch of rocks into cement. There's a real art to getting that mix right.
Oh, absolutely. The size and distribution of the particles, as well as the ratio of each ingredient, all play a crucial role in the final strength and durability of the concrete.
And speaking of strength, I remember reading in the textbook that concrete, while strong under compression, can be a little bit fragile under tension. What's the deal with that?
Yeah, that's a great point. Concrete is much better at resisting being squashed than being pulled apart.
Right.
That inherent brittleness can be a challenge, but engineers have developed some clever ways to reinforce it and overcome this limitation.
Okay, I'm intrigued. How do we make concrete even tougher? Do we just, add more cement?
It's a little more sophisticated than that. One common technique is using steel reinforcement, or what we call rebar. So Embedding steel bars within the concrete provides that extra tensile strength, preventing those cracks from spreading.
Okay.
And it's a win-win because steel's thermal expansion is similar to concrete's, meaning they expand and contract together without creating any internal stresses.
That's smart. It's not just about adding strength, it's about compatibility too.
What?
Other techniques are there?
Another approach is fiber reinforcement.
Okay.
So instead of those large steel bars, we mix in fibers, things like glass, steel, or even polymer fibers, directly into the concrete. Think of it like adding tiny threads throughout the material, creating a more interwoven and resilient structure.
So it's like reinforcing it from the inside out.
Exactly. These fibers help distribute the load more evenly and prevent those brittle cracks from propagating. It's a great way to, improve the overall toughness.
I'm seeing a pattern here. Engineers are like material matchmakers, finding the perfect partners to compensate for weaknesses. Are there any other tricks up their sleeve when it comes to concrete?
One more impressive technique is what we call pre-stressed concrete.
Okay.
And this involves intentionally introducing compressive stresses into the concrete before it's even subjected to loads. It's like giving the material a head start in the strength game, so to speak.
Prestressed concrete, that sounds intense. How does that actually work?
There are two main methods, pretensioning and post-tensioning. In pretensioning, steel wires are stretched within the concrete mold before the concrete's poured.
Gotcha.
Once the concrete hardens, the tension is released, and those wires try to contract, putting the concrete into compression. Post-tensioning works. It works similarly, but the tension is applied to the wires after the concrete has hardened.
Wow, that is some clever engineering.
Yeah.
It's amazing how understanding the properties of materials lets us, manipulate them in such sophisticated ways.
Exactly, and that's really just the tip of the iceberg when it comes to, the ingenuity involved in designing and engineering composites.
Okay, we've explored the world of particle-reinforced composites with concrete as our star example. Now, let's move on to the second major category you mentioned, fiber-reinforced composites. What makes them different and why are they so important?
So fiber-reinforced composites really take the concept of reinforcement to a whole new level. Here, the fibers themselves become the primary load-bearing components. They provide exceptional strength and stiffness. They're like the high-performance athletes of the composite world, capable of handling some incredible stresses.
It sounds impressive.
Yeah.
But what makes these fibers so special? Aren't all fibers basically the same?
Not at all. The type, the length, and the orientation of the fibers all play critical roles in determining the properties of the composite. It's not just about having fibers, it's about having the right fibers arranged in the right way to achieve those specific performance goals.
Okay, so it's all about strategy and precision. Tell me more about these high-performing fibers. What are they made of? And how do they work their magic within the composite?
Well, we can broadly classify the fibers into three categories: whiskers, fibers, and wires.
Okay.
So whiskers are like the elite athletes of the fiber world.
Okay.
There's single crystals, meaning that their structure is nearly perfect at the atomic level. And this perfection translates into incredible strength, but it also makes them the most expensive to produce.
So whiskers are like the Formula One race cars of fibers. Super high performance, but with a pretty hefty price tag.
Yeah, that's a great analogy. Then we have just fibers. These are more commonly used.
Okay.
They come in a wider range of materials,
Right.
everything from glass and carbon to aramids like Kevlar, boron, aluminum oxide, and silicon carbide.
Wow, that's a pretty diverse lineup. It
Yeah.
seems like there's a fiber for every occasion. But what about those wires? Where do they fit in?
So wires are basically larger diameter fibers.
Right.
They might not have the same extreme strength as whiskers, but they do offer good strength and stiffness, often at a more affordable price.
So we've got our star players, the fibers, but they can't do it alone, right? What about the matrix? What is its role in all of this?
You're absolutely right. The matrix, often referred to as the binder, is kind of like the unsung hero of the composite.
Okay.
It acts like the glue that holds everything together. It binds the fibers, it transfers loads between them, and it protects them from damage. It's like the team manager, making sure everyone works together smoothly and efficiently.
So it's not just about strength, it's about teamwork and support.
Precisely. A good matrix needs to be ductile, meaning it can deform under stress without cracking. It also needs to have, a strong bond with the fibers to ensure that efficient load transfer. Think of it like a good coach, one who knows how to, motivate and protect their players.
I like that analogy. The textbook mentioned that polymers are often used as matrix materials, especially with, with glass, carbon, and aramid fibers. What makes polymers so well suited for this role?
Polymers are a popular choice because they're lightweight, easy to process, and, relatively inexpensive.
Mm,
They also offer a good balance of properties, including strength, stiffness, and toughness.
okay.
Common polymer resins include polyesters, vinyl esters, epoxies, and polyamides.
Okay, so we've got our fibers and our matrix, but how do we actually put them together to create these high-performance composites? Is it like mixing ingredients in a bowl?
It's a little bit more sophisticated than that. There are various manufacturing techniques, and each is tailored to create specific types of composite structures. Three common methods are pultrusion, pre-preg production, and filament winding.
Those sound pretty high-tech. Can you give us a quick rundown of each process?
Sure. So let's start with pultrusion. It's a continuous process where fiber rovings, these are bundles of fibers, are pulled through a resin bath and then through a shaped die. The die forms the composite into the desired shape, and then the resin cures as it passes through, creating a continuous length of material.
So it's like a composite extrusion process, perfect for making things like rods, tubes, and beams.
You got it. It's a very efficient process, especially for, large-scale production. Now, pre-preg production is a bit different.
Okay.
It involves creating sheets of composite material that can then be molded into various shapes.
Right.
So continuous fiber tows are impregnated with a partially cured resin, and then they're pressed between sheets of paper to create this thin tape that we call pre-preg.
So it's like pre-made composite dough, ready to be baked into whatever shape you need.
Exactly. So manufacturers can cut and layer the pre-preg tape in different orientations to create, all sorts of complex shapes and really tailor the properties of the final product. It offers a lot of flexibility in design.
That's pretty fascinating. It's like building a custom-made composite puzzle.
What about filament winding? What kind of structures is that used for?
Filament winding is kind of like weaving a composite cocoon.
Oh, right.
So resin-coated fibers are wound around a rotating mandrel in this precise pattern.
Okay.
Once the desired number of layers is applied, the resin is cured and the mandrel is removed, leaving behind a hollow composite structure.
So it's ideal for creating things like pipes, tanks, and pressure vessels.
Precisely, and the precise control over fiber orientation during winding allows engineers to optimize that strength and stiffness of the final product.
It's amazing how these manufacturing techniques allow for, such fine-tuned control over the composite structure and its properties. It really highlights the engineering prowess behind these materials. Now, earlier you mentioned that the length of the fibers is crucial for fiber-reinforced composites. Why is that? Does size really matter in this case? Absolutely. Fiber length plays a critical role in how effectively loads are transferred from that matrix to the fibers themselves. There's even a term for it, critical fiber length.
Okay.
And if the fibers are shorter than this critical length, they won't be able to fully utilize their strength potential.
Okay, so it's not just about having fibers, it's about having fibers of the right length. Can you give us an analogy to help visualize this?
Sure. Imagine you're trying to pull a heavy object. Would you rather use short pieces of string or a single long continuous rope?
The long rope, for sure. It seems much more reliable.
Exactly. The long rope will transfer that force much more effectively. That's why continuous fibers, those that exceed that critical length, are so desirable in composites. They create a strong, uninterrupted pathway for the load to travel.
That makes perfect sense. So we need to think about fiber length, but what about their orientation? Does it matter if the fibers are all aligned in the same direction or if they're, randomly arranged?
That's a great question. The orientation of the fibers has a huge impact on the composite's properties. So aligned fibers create a material that is what we call anisotropic, meaning its properties vary depending on the direction.
Okay.
In the direction of fiber alignment, the composite is super strong, super stiff, but perpendicular to that direction, it's much weaker.
So if we want consistent strength in all directions, we'd need randomly oriented fibers.
Exactly.
Okay.
Randomly oriented fibers provide more isotropic properties, but there's a trade-off. The overall strength and stiffness won't be as high as with those aligned fibers. It really depends on the application and the specific properties needed.
It's like choosing the right tool for the job. Some tasks need that precise, powerful tool, while others might need something more versatile. And your source material actually includes some helpful diagrams illustrating these different types of fiber arrangements.
Yes. Figure 16.8 is a great visual aid. It shows those differences in mechanical behavior depending on whether the fibers are continuous and aligned, discontinuous and aligned, or discontinuous and randomly oriented.
Okay, so let's say we need like maximum strength in a specific direction.
Yeah.
What kind of real-world applications would demand that level of precision?
Think aircraft components. So in an airplane wing, for example, you want that maximum strength along the direction of flight to withstand those aerodynamic forces.
Right.
That's why unidirectional fiber alignment is often used in these in these high performance applications.
Okay.
And table 16.1 in the textbook really highlights just how dramatic the difference in longitudinal versus transverse strength can be.
Yeah, I can see how crucial that would be for something like an airplane wing. You definitely don't want any weak points in that structure.
Absolutely, but sometimes we need strength in multiple directions. That's where laminar composites come in. By stacking layers with different fiber orientations, we can achieve a more balanced strength in a plane.
That's a clever solution. It's like weaving a super strong fabric layer by layer to create a material that can handle stresses from all different directions. So we've talked about fiber length and orientation, but we haven't really discussed the unsung hero of the composite, the matrix. What are the key qualities of a good matrix material, and what are some common choices?
The matrix plays a vital role in holding everything together and making the composite work as a cohesive unit. It needs to be ductile, meaning it can deform under stress without cracking. It should also have a good bond with those fibers to ensure efficient load transfer. Think of it like a good team leader, one who can handle pressure, distribute tasks effectively, and keep everyone working together smoothly.
So it's not just about strength, it's about teamwork and flexibility.
Exactly. A good matrix needs to be adaptable and resilient, able to support those fibers and prevent cracks from spreading.
The textbook mentioned that polymers are often used as matrix materials, especially in combination with, glass, carbon, and aramid fibers.
Yeah.
What makes polymers so popular for this role?
Polymers are lightweight, easy to process, and relatively, inexpensive.
Yeah.
They also offer a good balance of properties, including strength, stiffness, and toughness.
Okay.
Common polymer resins include polyesters, vinyl esters, epoxies, and polyamides.
That makes sense. It seems like polymers are a pretty versatile choice for many composite applications. But what happens when we need a composite that can withstand higher temperatures? I'm guessing polymers have their limits?
You're right. For those high temperature applications, we turn to what we call metal matrix composites, or MMCs.
Okay.
These composites use a ductile metal, something like aluminum, magnesium, titanium, copper, or even superalloys as the matrix. And these metals can handle much higher temperatures than their polymer counterparts.
So it's like upgrading to a more heavy-duty team for those extreme conditions.
Exactly. Table 16.5 in the textbook actually shows how the properties of different fiber-reinforced epoxy composites can vary, emphasizing the need to carefully select the right combination for those specific operating conditions. And the source material even mentions high-temperature thermoplastics like PEEK, PPS, and PEI as potential players in this field.
It's fascinating how this field of composites is constantly evolving, pushing the boundaries of performance. And it's not just about making things stronger. It's about tailoring those properties for specific needs, much like we discussed with concrete earlier.
Absolutely. And speaking of tailoring properties for specific needs, let's move on to a particularly interesting type of composite. Ceramic matrix composites, or CMCs.
Okay.
These composites aim to improve the fracture toughness of ceramics, which are known for their high temperature resistance, but also for their brittleness.
So we're trying to make an already heat-resistant material even tougher? That sounds challenging. How do we go about doing that?
By incorporating particles, fibers, or whiskers into that ceramic matrix, we can actually hinder crack propagation and make the composite, more resistant to fracture. It's like giving the ceramic a safety net to prevent those brittle cracks from spreading.
It's a clever approach.
Yeah.
So instead of just, accepting the brittleness of ceramics, we're finding ways to enhance their toughness and make them even more useful.
Exactly. One fascinating technique is what we call transformation toughening, where particles of zirconia undergo a phase change under stress.
Okay.
And this phase change actually creates compressive forces that help stop those cracks from growing.
Wait, so the material's actively fighting back against the cracks? That's incredible.
It is. And then by adding silicon carbide whiskers to the mix, we can further enhance that toughness. Table 16.10 in the textbook actually shows how increasing whisker content can significantly improve both fracture strength and toughness.
I'm amazed by how we can engineer a material to become tougher by carefully selecting and arranging its components. It's like building a fortress, brick by carefully chosen brick.
Yeah, it's a fascinating interplay between those material properties and structural design. And speaking of intriguing materials, let's talk about carbon composites. They sound almost futuristic.
They do sound high-tech. What makes them so special?
So carbon composites use carbon fibers in a carbon matrix. This creates a material that boasts incredible high temperature strength and stiffness.
Wow.
They have incredibly low thermal expansion, high thermal conductivity, and good fracture toughness.
Wow, they sound like they can handle anything. What are they actually used for?
These properties make them ideal for demanding applications like rocket nozzles, brake linings for high-performance aircraft, and even components for nuclear reactors.
Okay.
They can withstand those extreme temperatures and stresses.
They sound almost indestructible. But I bet there's a catch. They must be expensive to produce.
You're right; they are expensive due to that complex processing involved. But
No.
their exceptional properties often justify the cost, especially in those critical applications where failure is not an option.
Okay, so we've explored the world of particle reinforced, fiber reinforced, and even ceramic matrix composites. You mentioned a third main category earlier, structural composites. What's the difference between these and the ones we've already talked about?
Structural composites take things to a larger scale, literally.
Okay.
They involve combining different types of composites and even homogeneous materials to create, larger, more complex structures.
Like,
Think building components, aircraft wings, or even the body of a race car.
wow.
Two common examples are what we call laminar composites and sandwich panels.
Okay, I'm picturing building-sized composites here. Tell us more about these structural marvels.
Laminar composites are essentially stacks of layers, each with a different fiber orientation, bonded together to create a material that's nearly isotropic in a plane,
Okay.
meaning it has similar properties in all directions within that plane.
So it's like taking the concept of fiber orientation to a whole new level.
Precisely. Figure 16.1 in the textbook provides a great visual representation of this. Now, sandwich panels are ingeniously designed to provide high stiffness and strength at a low weight. They consist of two strong outer faces, often made from materials like aluminum, fiber-reinforced plastics, or even plywood, and they're separated by a lightweight core.
It's a super strong sandwich.
Yeah.
What's the core typically made of?
The core can be made from a variety of materials, including rigid polymeric foams, wood, or even honeycombs.
Honeycombs, like the ones bees make.
Yes, but in this case, they're made from thin foils formed into these interlocking hexagonal cells. This honeycomb structure provides excellent strength and stiffness at a very, very low weight, which is why sandwich panels are so popular in applications where weight is a critical factor, like aerospace and transportation. Figure 16.18 in the text shows how these honeycomb core sandwich panels are constructed.
That's fascinating. It's like taking inspiration from nature to design, efficient structures. So where do we actually see these sandwich panels in action?
Sandwich panels are incredibly versatile. They're used in everything from building panels and aircraft components to even the modern ski.
Wow, I had no idea those skis were so high tech.
Yeah.
It's amazing how composites are kind of hidden in plain sight all around us.
They are.
We've covered a lot of ground here, from the basic principles of composites to the different types and their amazing applications.
Yeah, it's been quite a journey through the world of composite materials. And we've only just scratched the surface. There's so much more to explore in this constantly evolving field.
Absolutely. I'm already thinking about all the incredible possibilities for the future. But before we get ahead of ourselves, let's take a step back and talk about one final category of composites that we haven't discussed yet. Hybrid composites. What makes these composites unique?
Hybrid composites are all about combining the best of different worlds.
Okay.
bringing together at least two different types of fibers within a single matrix.
Right.
It's like assembling a dream team of fibers, each contributing its own unique talents to create a material with truly exceptional properties.
So it's like the ultimate composite collaboration.
Exactly. For
Okay.
example, a common hybrid combines carbon fibers for that strength and stiffness with glass fibers for cost effectiveness and toughness.
Okay.
By strategically blending these fibers, engineers can achieve a balance of properties that wouldn't be possible with a single fiber type.
It sounds like the possibilities for customization are endless with hybrid composites.
Yeah.
We can literally handpick the fibers we want to create a material that's perfectly suited to a specific application.
That's the beauty of hybrid composites.
Yeah.
They offer this remarkable level of flexibility in tailoring properties to meet those specific needs. And this ability to customize is one of the key reasons why composites are becoming increasingly popular in a wide range of industries.
Well, I have to say, this deep dive into the world of composites has been a real eye-opener.
Yeah.
We've gone from understanding the basic principles to exploring a wide range of composite types, manufacturing processes, and even the strategies behind their design.
Yeah.
It's incredible to see how human ingenuity and material science come together to create these amazing materials that are shaping our world.
It's been a fascinating journey, and it's truly remarkable how composites are revolutionizing industries from aerospace to construction to sports equipment. And as research and development continue, we can expect to see even more incredible advancements in the future.
Absolutely. And that brings us to a final thought-provoking question for you, our listener. As scientists and engineers continue to develop new types of composites and push the boundaries of what's possible, what incredible new materials and technologies might we see in the future? Imagine lighter, stronger cars, more efficient aircraft, and even self-healing structures.
Yeah, wow.
The possibilities are practically endless. Now that you have a better understanding of how composites work, keep an eye out for them in the world around you. You might be surprised at how many places they pop up.
You really might.
It's amazing to think about all the different ways we can engineer these fibers and matrices to create composites with such specific properties.
Yeah.
But what about the big picture? How are these composite materials actually being used to change the world around us?
That's where things get really exciting. Composites are revolutionizing countless industries, everything from aerospace and automotive to construction and even sports equipment. Their lightweight yet strong nature is a real game changer. It allows us to build things that were previously unimaginable.
Okay, I'm ready for some real-world examples. Where are composites making the biggest impact?
Let's start with aerospace. Modern aircraft rely heavily on composites for their wings, fuselages, and other structural components. These materials offer a significant weight reduction compared to traditional metals like aluminum. And this leads to improved fuel efficiency and reduced emissions.
Well, composites are helping us fly farther and greener. That's a win-win.
Absolutely. And it's not just about weight savings. Composites also offer excellent fatigue resistance. This means they can withstand repeated stresses without weakening over time. And that's crucial for aircraft that experience, constant vibrations and pressure changes during flight.
It's like they're built for the long haul. What about the automotive industry? Are composites making their way into our cars as well?
Definitely. Car manufacturers are increasingly using composites to create lighter and more fuel-efficient vehicles. You'll find them in body panels, bumpers, dashboards, and even structural components like chassis and suspension parts.
I've heard about carbon fiber being used in some high-performance sports cars. Is that a type of composite?
Yes, carbon fiber is a popular choice for high-end vehicles because of its exceptional strength to weight ratio. It's a type of fiber reinforced composite where carbon fibers are embedded in a polymer matrix, typically an epoxy resin.
So it's like the elite athlete of composite materials, bringing both strength and lightness to the game.
Exactly. Carbon fiber composites are incredibly strong and stiff, but they're also very lightweight, making them ideal for applications where performance is really paramount.
It sounds like composites are giving those sports cars a serious competitive edge.
Yeah.
But what about everyday vehicles? Are composites finding their way into more affordable cars as well?
Absolutely. So while carbon fiber might be reserved for, for those high performance vehicles, other types of composites like glass fiber reinforced polymers are becoming increasingly common in those mass produced cars.
Right.
They offer a good balance of strength, weight savings, and cost effectiveness, which makes them a viable option for a wider range of vehicles.
It's amazing how these materials are like making their way into all these different aspects of our lives,
Yeah.
off without us even realizing it. What about the construction industry? I imagine there's some pretty interesting applications for composites there too.
You're right. Composites are making a significant impact on construction. They're used for everything from structural beams and columns to cladding and roofing materials.
Okay.
Their resistance to corrosion, moisture, and insects makes them ideal for those outdoor applications, and their lightweight nature simplifies installation and reduces those transportation costs.
So they're not only strong and durable, but also practical and cost-effective in the long run.
Exactly. And there's a growing trend towards using composites for those sustainable building practices. Their lightweight nature can actually reduce the overall weight of a structure, which leads to smaller foundations and less energy consumption during construction.
It sounds like composites are helping to create a greener and more efficient construction industry. What about other areas? Are there any surprising applications for composites that I might not be aware of?
Composites they're popping up in all sorts of unexpected places. For example, they're used to make wind turbine blades, where their strength and stiffness allow for larger and more efficient blades to capture more of that wind energy.
Right.
They're also found in sporting goods, everything from tennis rackets and golf clubs to bicycles and skis, where their lightweight and high performance properties really enhance athletic performance.
I never would guess that my tennis racket could be made from like the same type of material as an airplane wing. It's amazing how versatile these composites are.
It is. And that's really just the tip of the iceberg. As research and development continue, we can expect to see even more innovative applications for composites in the future. They truly have the potential to transform the way we design and build everything around us.
Okay, so we've talked about how composites are being used to make, everything from airplanes and cars to buildings and sports equipment. But what about the future? What are some of the most exciting areas of research and development in the world of composites?
There's so much happening in the field right now. It's hard to know where to begin. One exciting area is the development of self-healing composites.
Uh-huh.
These materials have the ability to repair damage on their own, much like our bodies heal from injuries. This could revolutionize industries where durability and longevity are paramount, such as aerospace and infrastructure.
Self-healing composites. That sounds like something out of a science fiction movie. How does it even work?
Researchers are exploring, various approaches. One method involves embedding tiny capsules filled with a healing agent within the composite. So when the material is damaged, those capsules rupture, releasing that healing agent, which then reacts to seal the crack or repair the damage.
So it's like the composite has its own like built-in repair kit. That's incredible. What other advancements are on the horizon?
Another fascinating area is the development of what we call bio-based composites.
You're right.
These materials use renewable resources, things like plant fibers or bio-based resins, as their building blocks, which offers a more sustainable alternative to those traditional petroleum-based composites.
So we're not only making stronger and more efficient materials, but we're also making them more environmentally friendly.
Oh,
that's fantastic.
Absolutely. Sustainability is a key driver in composite research and development. And as the demand for those eco-friendly materials continues to grow, we can expect to see even more innovation in this area.
It's inspiring to think about how composites are contributing to a more sustainable future. What about the other end of the spectrum? Are there any advancements focused on like pushing the limits of performance?
Definitely. One area that's receiving a lot of attention is the development of what we call nanocomposites. These materials incorporate nanoparticles into either the matrix or the reinforcement phase.
Okay.
And this leads to significant improvements in properties like strength, stiffness, and thermal conductivity.
Nanoparticles. That sounds like we're entering the realm of the The ultra tiny.
We are, and the potential of nanocomposites is just it's enormous. They could lead to the development of materials with unprecedented strength to weight ratios, enabling us to, enabling us to build lighter, stronger, and more efficient structures than ever before.
It sounds like nanocomposites could be a real game changer for industries like aerospace, where every ounce of weight saved translates into, increased fuel efficiency and performance.
Precisely. And as our understanding of nanomaterials continues to grow, we can expect to see even more remarkable advancements in the realm of nanocomposites.
This deep dive into composites has taken us from the basic principles to real-world applications, and even a glimpse into the future. It's clear that these materials are not only changing the way we build things, but also inspiring new possibilities for innovation and sustainability.
You really are.
And it's been a fascinating journey, and it's truly remarkable to see how composites are shaping the world around us. And as research and development continue, we can expect even more incredible advancements in the future. It's fascinating to think about, the ripple effects of these materials and how they're not just changing industries, but also like prompting us to think differently about, design, sustainability, and even ethics.
You've hit the nail on the head there. Composites are really forcing us to reimagine what's possible, but they also challenge us to consider the consequences of those possibilities.
Okay, I have one last question that's been kind of like nagging at me. Throughout this whole deep dive, we've explored all these different types of composites, but we haven't really talked much about how they're actually like joined together. I mean, we can create these amazing individual components, but how do we assemble them into larger functional structures?
That's a crucial aspect of composite design and manufacturing. Joining composites effectively is essential for ensuring that that structural integrity and reliability of the final product.
So we can't just use like glue or screws like we might with traditional materials?
It's a bit more complicated than that.
Okay.
Composites often require specialized joining techniques that really take into account their unique properties and behavior.
Okay, I'm all ears. What are some of the common methods for joining composites?
There are several approaches, each with its own advantages and limitations. One common method is what we call adhesive bonding. And here, a specialized adhesive is used to create that strong bond between the composite components. This technique is particularly well suited for joining large, flat surfaces or components with complex geometries.
So it's like creating this super strong glue joint that
Yeah.
can handle the stresses and strains that composites experience.
Exactly. Adhesive bonding offers a number of advantages, including high strength, good fatigue resistance, and the ability to distribute loads evenly across that bonded area. However, it also requires careful surface preparation and precise application of the adhesive to ensure a reliable bond.
It sounds like there's a real art to adhesive bonding, requiring both knowledge of the materials and skill in the application process. What other techniques are used?
Another common approach is what we call mechanical fastening. This involves using bolts, rivets, or other mechanical fasteners to join those composite components. And this method is often preferred for applications where high strength and rigidity are required, such as in load-bearing structures.
It was like creating a traditional bolted joint, but with composites.
Yes, but there are some important considerations.
Okay.
When using mechanical fasteners with composites, it's crucial to select the appropriate fastener type and material, as well as to design the joint carefully to avoid stress concentrations that could lead to premature failure.
It sounds like joining composites requires a pretty deep understanding of both the materials and the mechanical principles involved.
Absolutely, and there's this constant drive to develop new and improved, joining techniques that are more efficient, more reliable, and more cost effective.
What are some of the emerging trends in composite joining?
One area that's gaining traction is the use of welding techniques, specifically for thermoplastic composites.
Okay.
So these composites can be melted and fused together, which creates a a strong and seamless joint.
So it's like welding metals, but with composites.
Precisely. Welding offers a number of advantages, including high joint strength, fast processing times, and the potential for automation.
It sounds like welding could be a real game changer for joining those thermoplastic composites, especially in those high volume manufacturing applications.
Absolutely. And as research and development continue, we can expect to see, even more innovative joining techniques that really push the boundaries of what's possible with composite materials.
This deep dive into the world of composites has been a truly incredible learning experience. We've covered so much ground, from the basic principles and types of composites to the fascinating ways they're being used and the challenges of, manufacturing and joining them. But what really stands out to me is this, the sense of endless possibility.
I agree. The field of composites is constantly evolving with new discoveries and innovations emerging all the time. It's an exciting time to be involved in this field, and I can't wait to see what the future holds.
It's truly inspiring to think about how these materials are shaping the world around us,
Yeah.
enabling the creation of lighter, stronger, and more efficient structures that are changing the way we live, work, and play. As scientists and engineers continue to push the boundaries of what's possible with composites, who knows what incredible innovations lie ahead? Perhaps we'll see self-healing bridges, space elevators made from these ultra lightweight materials, or even personal flying vehicles that are both safe and affordable. The possibilities are truly endless, limited only by our imagination and our commitment to exploring the full potential of these remarkable materials. And with that, I think we've reached the end of our deep dive. I want to thank you, our expert, for sharing your knowledge and insights with us today.
It's been my pleasure. I hope our listeners have enjoyed this journey into the fascinating world of composites, and remember, keep an eye out for these materials as you go about your day. You might be surprised at how many places they're already making a difference.